Question 4. A part. Explain in a four common feature engineering technique for continuous or categorical data. Answer. Feature engineering involved creating new input feature from existing one to help machine learning model perform better. Here are four common techniques applicable to the continuous or categorical data. First is imputation. This technique handles the missing value in a dataset. For the continuous data, missing value are often replaced by the mean, median, or a specific value depending on the data's distribution and the reason for the missingness. For the categorical data, missing value can be imputed with a mode, a most frequently category, or the new category like unknown to preserve the information that the value are missing. The second is one hot encoding for the categorical data. This method convert categorical variable into a numerical format that machine learning algorithm can understand. It creates new binary column for each unique category present in the original format. If a data point belongs to a specific category, the corresponding new columns get a value of 1 and the all other get 0. Beaning. This involves converting continuous data into categorical group or a bean. For example, a continuous features like age might be beaned into child 0 to 12, teen 13 to 19, adult 20 to 65, and senior 65 plus. This can help simplify the model and handle non-linear relationship. The fourth is feature scaling for continuous data. While technically a data processing step, it often falls under feature engineering as it standardizes the range of independent continuous feature. Common method include max and min scaling, rescaling a data to a fixed range, usually 0 to 1. Standardization Z-square scaling rescales the data to have a mean of a 0 and standard deviation of 1. This is crucial for the algorithm sensitive to a scale of input feature such as k nearest neighbor or a support vector machine. Question number 4 B part. What is sampling form of distribution? Express inverse transform sampling or Monte Carlo sampling with an example. Answer. Sampling from a distribution means generating random value that follows a specific probability distribution such as uniform, normal, exponential, etc. It used in simulation, probabilistic modeling, statistic analysis, and machine learning. Example, if one sample from a normal distribution, the generated value will follow the bell-shaped curve. Monte Carlo sampling. Monte Carlo sampling is a method that uses random sample to approximate. First is numerical result, probabilities, integral, and value of mathematical expression. It is especially useful when formula too difficult to solve analytically. Key idea is generate many random sample, then observe a outcome, and then use average to estimate a desired value. The Monte Carlo sampling steps are first choose a problem or a quantity to estimate. The second, then generate many random samples using a simple distribution of one uniform. Third, apply a rule slash function to each sample. Fourth, take the average of a result. Then this approximates the true value. Monte Carlo example estimate the value of pi. Method draw a random point inside a 1 into 1 square. A quantus circle of a radius 1 fit inside a square. For each random point x comma y x comma y x comma y, check if it lie inside the quantum circle. X square plus y square smaller than 1. Let n and n equals to total point, m equals to point inside a quarter circle. The Monte Carlo estimates of pi equals to pi approximately equals to 4 into n by m. Example numericals. Suppose we generate 10 random points and 8 of them fall inside a circle. Then pi approximately equals to 4 into 8 by 10 equals to 3.2, which with more point like 10,000 estimate become more accurate. Question A part is distinguish between parametric versus non-parametric models and supervised and non-supervised learning with example. Parametric models are make strong assumptions about data distribution. Example normality. Non-parametric model make fewer assumption about data distribution, more flexible. Parametric model have a fixed number of parameter, model structure is set. Non-parametric model has variable number of parameters, structure adopt to data. Parametric model can work with a less data, efficient for a large data set with a few features, whereas non-parametric models require more data, conceptual, computationally intensive. Parametric model is less flexible, prone to overfitting complex data, whereas non-parametric is high flexible, better for complex non-linear relationship. Example of parametric model is linear regression, logistic regression, whereas of non-parametric model is decision tree, k nearest neighbor, knn method. The second distinguish between supervised learning and unsupervised learning. The supervised learning uses a labeled data input and output pair. The unsupervised learning uses a unlabeled data, no predefined output. Supervised learning predict output of a new input learn mapping functions, whereas non-supervised learning discover hidden pattern structure or a grouping in a data. Supervised learning teachers provide correct answers, model learns from a mistake, whereas in non-supervised learning finds pattern autonomously, no direct feedback or correctness. Supervised learning example are email spam detection, image classification, cat/dog. A supervised learning example is customer segmentation clustering, dimensionality reduction PCA. Question number 5. B part define accuracy, precision, recall, F1 score and illustrate this computation using a confusion matrix. The predicted yes and the actual yes intersect, then it will give true positive TP. If actually actually it is yes but a prediction is no, then it is false negative. If it is actually no and the predicted is yes, then it is false positive. And if its predicted is no and actual is also no, then true negative TN. Accuracy measure overall correctness. Accuracy equals to TP plus TN upon TP plus TN plus FN plus FP. Precision, how many predicted positive are actually correct. Precision is true positive upon true positive plus false negative. Recall, sensitivity, recall equals to true positive upon true positive plus false negative. It is how many actual correct positives are correctly predicted. F1 score, harmonic mean of precision and recall. Useful when a data is imbalanced. F1 equals to 2 into precision into recall upon precision plus recall.